In the heart of the United Kingdom's busiest financial district, where every square meter is constrained by history, traffic, and strict heritage preservation regulations, London built a skyscraper that captured the attention of the entire engineering world. That building is the Leadenhall Building, a 225-meter tower with a distinctive slope design, famously nicknamed the Cheese Grater of London. But what makes this structure truly remarkable is not its height. It is the way it was built, using a series of advanced construction techniques never before executed at such a scale in one of Europe's oldest financial centers. In this video, join Mandarin Tech as we explore how this city created one of the world's most daring skyscrapers. The Leadenhall Building was designed by architect Richard Rogers and completed in 2014. Thanks to its distinctive sloped shape, with the structure narrowing toward the top like a giant cheese grater, the tower was given the popular nickname, the Cheese Grater, by the people of London. However, this design was not created simply for aesthetics. It was specifically shaped to protect the viewing corridor toward St. Paul's Cathedral, one of the most important historical and religious landmarks in the United Kingdom. The tower is located in a prime area of the City of London, bordered by Leadenhall Street to the south and St. Helens Square to the east. This district is densely packed with financial buildings, commercial developments, and high-rise office towers. Because of that, the Leadenhall Building is not only an architectural icon, but also a carefully planned project designed to meet the needs of modern businesses. To better suit the extremely confined construction conditions in the heart of London, the engineering team had to change almost the entire traditional skyscraper construction process. Instead of fabricating and assembling most of the structure directly on site, the majority of the Leadenhall Building's massive steel components were prefabricated in factories located in northern England, hundreds of kilometers away from London. This approach helped reduce noise, limit dust, minimize the number of workers needed on site, and improve safety for nearby residents as well as the surrounding transportation network. At the factories, enormous steel columns and structural beams were cut, pressed, bent, and manufactured with extremely high precision so they could withstand the massive loads of a building rising more than 220 meters tall. After the structural shaping process was completed, the components were transported to other specialized facilities where they underwent several surface treatment stages, including sandblasting for cleaning, anti-corrosion primer coating, and the application of special fireproof materials designed to improve heat resistance during a fire. Moving almost the entire manufacturing process away from the construction site not only increased accuracy and construction speed, but also became an almost mandatory solution for this project. The Leadenhall Building is located in London's densely packed financial district, where the streets are extremely narrow, traffic density is very high, and there is almost no available space for material storage or for operating a traditional large-scale construction site. When the first steel components arrived at the construction site, the frame erection process began almost like assembling a giant machine. Every steel column, horizontal beam, and diagonal brace was lifted into place by cranes, carefully aligned and secured using high-strength steel connections. Each component not only had to match the exact dimensions, but also had to be installed in the correct sequence, because the entire building functioned as a highly interconnected structural system. The sloped shape of the Leadenhall Building made the erection process even more complicated. Instead of rising like a simple vertical box, the tower gradually narrows as it gets taller in order to preserve protected views of St. Paul's Cathedral. As a result, every floor, every column, and every diagonal brace had to fit within a constantly changing geometry. Even a small deviation near the bottom could cause the upper sections of the tower to shift away from their intended position. To control this, engineers had to predict in advance how the steel frame would deform during construction. As new floors were added, the weight of the building itself caused the steel structure to move and gradually adjust under load. Because of this, some components were not manufactured to match the final visible position shown on the drawings. Instead, they were intentionally fabricated with calculated compensation offsets already built in. As the full weight of the structure was gradually transferred onto the frame, the building would slowly settle into its correct final alignment. After each new group of floors was installed, the entire structure had to be inspected, surveyed, and recalibrated to ensure the tower continued following its intended shape. The next stage was the installation of the floor systems for each level. Engineers used prefabricated floor modules in which many structural elements, technical systems, and floor sections had already been integrated at the factory. When transported to the construction site, they were no longer loose construction materials but more like pre-engineered modules with carefully calculated positions, dimensions, and installation sequences. This allowed each floor unit to be lifted into place by crane, positioned accurately, and then connected to the building's main steel structure. The entire office floor system was suspended and connected to the external perimeter steel frame. Although the floor plates had a rectangular shape, their depth gradually decreased as the tower rose higher, matching the building's distinctive slope profile. According to the architectural design, each office floor became approximately 750 millimeters narrower as it moved closer to the top of the tower. Every floor not only had to meet the correct elevation, position, and load requirements, but also had to align precisely with the constantly changing angle geometry of the entire structure. To control this, some of the inclined steel members along both sides of the tower were intentionally fabricated shorter in order to pull the megaframe back toward a vertical alignment. This adjustment process began when the building reached level 19 and was repeated after every additional 7 floors. One of the biggest differences of the Leadenhall Building lies in the way its elevator system and service core were designed. In most skyscrapers, the elevators, emergency staircases, mechanical pipes, restrooms, and operational systems are typically placed inside a massive concrete core located at the center of the building. This approach helps stabilize the structure, but it also consumes a large amount of usable interior space. Leadenhall took a different approach. The entire main service core was separated from the office spaces and positioned along the north side of the tower. This core contains passenger elevators, freight elevators, mechanical and electrical systems, utility pipes, restrooms, and many of the operational facilities required for each floor. As a result, the office spaces inside the building were opened up as much as possible, creating large flexible floor plates with far fewer obstructions from columns or concrete cores. The building's elevator system was also divided into multiple groups serving the lower, middle, and upper floors separately. One of the most striking features is that many of the elevators are placed within an exposed external core, becoming part of the building's architectural identity. Pedestrians can actually see the elevator cabins moving behind the glass facade, almost like watching the mechanical components inside a giant machine. However, because the building does not rely on a traditional central concrete core, installing the elevator system became far more complicated. All electrical wiring, control equipment, and technical components had to be carefully hidden within the rear walls and floor systems in order to preserve the minimalist appearance and maintain the project's design philosophy, where the structure itself also becomes the architecture. After the steel frame, floor systems, and service core were fully installed, the Leadenhall Building entered the final stage of completing its exterior envelope and interior spaces. The tower was then covered with a transparent glass facade. Inside the office areas, the design had to solve several challenges at the same time, including thermal insulation, natural lighting, solar radiation control, and overall comfort for the people working inside the building. To achieve this, the outer glass layer was combined with an additional inner layer of glazing, creating a cavity space that contains a structural framing and automated sun-shading blinds. These blinds inside the glazing cavity can automatically adjust to reduce heat and glare when sunlight becomes too intense. At the lower levels of the tower, the design was handled in a very different way. Instead of occupying the entire ground level like many commercial skyscrapers, the base of the Leadenhall Building was cut back diagonally, creating a large public space approximately 7 stories high beneath the tower. This allowed the Leadenhall Building to become more than just a sealed office skyscraper. It created a rare open breathing space within London's dense financial district. Beneath the tower, pedestrians can walk through the open area, stop to observe the enormous exposed steel structure above them, and experience the true scale of the building directly from the street level. However, before the massive steel frame of the Leadenhall Building could rise above London, engineers first had to solve the most critical challenge beneath the ground, the building's foundation. The site previously contained an older office tower, built in 1969, with a massive concrete core located at the center of the property. Construction crews had to carefully demolish the entire structure while tightly controlling vibration, dust, and noise to avoid affecting the surrounding buildings in London's busy financial district. Once the site was cleared, engineers began constructing a new foundation and basement system capable of supporting the entire 225-meter skyscraper. Unlike most traditional skyscrapers that rely on a huge central concrete core, the Leadenhall Building was designed with an external steel megaframe surrounding the structure. This giant steel system would carry the vertical loads of the floors, resist strong wind forces, and stabilize the tower's distinctive sloped shape. The most distinctive feature of the Leadenhall Building is that its shape was not created simply to make the tower look unusual. It was born from one of London's strict urban limitations. In this city, important protected sight lines towards St. Paul's Cathedral are strictly preserved. This meant that a new skyscraper could not simply rise upward and block the historic dome of the cathedral. As a result, instead of building a conventional vertical tower, the architects designed a structure that gradually slopes backward as it rises. The higher the building goes, the narrower it becomes, allowing the protected view of St. Paul's Cathedral from Fleet Street to remain visible. This preservation requirement ultimately created the tower's famous nickname, the Cheese Grater. But behind its cheese grater-like appearance was a chain of highly complex engineering decisions. The service core had to be pushed to the exterior. The steel megaframe had to become the primary stabilizing structure. The floor plates had to gradually shrink with height, and the entire structural system had to be calculated like a giant three-dimensional space frame. At Leadenhall, architecture and engineering became almost impossible to separate. The sloped form dictated the structure dictated the construction method, and the construction method determined how every component would be fabricated, transported, and assembled. That is why this project stands out not only because of its appearance, but because nearly the entire way it was built had to be redesigned to fit within a narrow construction site, a highly sensitive skyline, and a city that did not allow engineers to do things the easiest way possible. The Leadenhall Building demonstrates how a historic city like London can embrace modern skyscrapers without completely destroying its architectural heritage. In a dense financial district filled with narrow streets, protected landmarks, and strict planning regulations, the challenge was not simply to build taller, but to create a modern tower capable of coexisting with the city's centuries-old history. To achieve this, engineers developed a structure with its distinctive sloped form, exposed steel megaframe, and large-scale prefabrication strategy. More than 18,000 tons of steel were used for the main structure, with thousands of components manufactured off-site before being transported into central London for precise assembly. This approach helped reduce noise, minimize traffic disruption, and limit the project's impact on the surrounding area. From an engineering perspective, Leadenhall showed that future skyscrapers may no longer rely entirely on traditional on-site construction. Instead, they can function like giant modular systems, where logistics, 3D modeling, and precision manufacturing become just as important as the construction site itself. The Leadenhall Building is not the tallest skyscraper in Europe, nor the most structurally complex building ever created. Yet from a narrow construction site in the heart of London, engineers managed to build a tower without relying on the massive traditional concrete core used in most modern skyscrapers. Because of that, the Leadenhall Building became more than just the cheese grater on London's skyline. It became proof that in modern construction, limitations do not always restrict creativity. Sometimes those limitations are exactly what force engineers and architects to create their boldest solutions. What do you think about the way London built a modern skyscraper while still protecting the historic view of a centuries-old cathedral? Leave your thoughts in the comments below. And don't forget to like, share, and subscribe to Mandarin Tech for more incredible engineering stories and mega projects from around the world.